We have one more test we can do with the second derivative, and this is called the second derivative test for local extrema. Okay, so for this, we're looking at places where the first derivative equals 0. Okay, so where f prime of c equals 0, notice that that is a critical point of the function of f of x. So you're already starting with looking at a critical point. Then, if you're at that critical point and f double prime of c is greater than 0, let's sketch this out here. Okay, let's say this is your point right here. And at that point c, okay, we have a derivative of 0. So that would make a horizontal tangent line. And then this part here, f double prime of c being greater than 0, that's a positive second derivative. Positive second derivative leads us to a concave up type of shape for our function. So we have a horizontal tangent line and a concave up type of shape. So remember, positive, happy face, concave up. So if this right here is our point C, we can see that on that function, C is a local minimum. It's at the bottom of that valley, okay? So it is lower than all the other function values around it. So yeah, we have a critical point with a positive second derivative, and that creates a local minimum. Now, if we've got that same type of situation, we've got a critical point here with a nice horizontal tangent line, f prime of c equals 0. Okay, so there's our point C. Nice horizontal tangent line. Okay, f prime of c equals 0. And we're also given here that the second derivative is negative, less than 0. So negative means concave down, frowny face type of shape. Okay, so there's our critical point with the horizontal tangent line, and we have a concave down type of shape here. So we can see there that C, and f of c specifically, is going to be a local maximum value of the function. It's at the top of the hill there. All right. So we can identify local minimums and local maximums also based on the second derivative. Now, you can also do this, remember with our first derivative test, you look at where the first derivative goes negative and then switches to positive. Okay, so negative first derivative showing decrease, positive first derivative showing increase. That gives you a local minimum. Okay, that still totally works. All right, this is just another way of testing that. Same type of thing for this. If your first derivative is positive and then switches to negative after that critical point, that means the function was increasing and then it started decreasing. That also shows you a local maximum there. So the first derivative test still totally works. This is just an alternative. Now, if your first derivative equals 0, so you've got a critical point there, and the second derivative also equals 0, then we don't really have a concave up or concave down situation here. This might be an inflection point maybe, but the point here is that we can't really tell what's going on with this. There's no clear picture that you can draw. So in this case, we just say that the second derivative test actually doesn't apply to that case. The test fails us. So you would have to go back and use your first derivative test or some other technique. So use first derivative test or some other method. for looking at this, because you might have a minimum, you might have a maximum, or it might be neither. So if the second derivative equals 0, if you can't tell about concavity, then we don't really have a nice conclusion for that one. But for the other two cases, a critical point with either a positive second derivative or a clear negative second derivative, then yeah, you can identify your local extrema using that.